Hello there, and welcome to Earth's History, where we trace the threads of cosmic events that shaped our world, where we look up at the night sky and ask questions about the celestial companion that has watched over Earth for billions of years. Tonight, we're traveling back to witness the most violent, spectacular, world-shattering event in our planet's history, the birth of the moon. This is the story of collision and creation, of destruction and rebirth, of how a Mars-sized world named Theia smashed into the young Earth, and from that catastrophic impact, our moon emerged. If you've ever looked up at the full moon and wondered where it came from, if you've ever felt its pull, literal and metaphorical, and pondered its origins, if you've ever been awed by eclipses or moved by moonlight, you're about to discover something profound. The moon wasn't always there. There was a time, early in Earth's history, when our sky was empty at night, when no large companion hung overhead, when Earth spun alone through space. And then, in a matter of hours, everything changed. A collision occurred that was so powerful, so transformative, that it melted both worlds, threw debris across space, reshaped Earth entirely, and created the moon that now lights our nights. Wherever you are right now, I hope you're comfortable, settled, ready to journey back 4.5 billion years to witness the most dramatic moment in Earth's history. Maybe you're lying in bed with moonlight streaming through your window. Maybe you're sitting quietly as darkness falls and the moon rises. Maybe you're in that peaceful space where the day's concerns fade and you can contemplate deep time, cosmic violence, the accidents that shaped our world. If this journey into Earth's violent past brings you wonder, if it helps you see the moon differently, if it connects you to the grand story of our planet's formation, I'd be grateful if you'd like the video, subscribe to the channel, or share it with someone else who looks up at the moon and wonders. So settle in. Let your breathing slow, like the gradual cooling of molten rock. Let your thoughts drift like debris in orbit around a shattered world, and let's begin. Because 4.5 billion years ago, in the chaotic early solar system, two worlds were on a collision course. Earth, still forming, still growing, still hot from its own assembly, and Theia, a planet perhaps the size of Mars, wandering through the inner solar system on an orbit that would intersect with Earth. They were not aiming for each other. Gravity doesn't aim, doesn't plan, doesn't intend. But mathematics is inexorable, physics relentless. The orbits converge, the distance closed, and one day, one fateful, terrifying, transformative day, Theia struck Earth in a glancing blow that would change both worlds forever. Before we can witness that collision, before we can understand what happened when Theia met Earth, we need to understand the world into which this catastrophe occurred. We need to go back to the very beginning, to the birth of the solar system itself, to understand how planets form, why collisions were common, why the early solar system was a violent, dangerous place where worlds grew through impacts, where the survival of any planet was uncertain. Our story begins 4.6 billion years ago, give or take a few tens of millions of years. The solar system didn't exist yet. In its place was a molecular cloud, a vast region of gas and dust drifting through space, cold and dark, composed mostly of hydrogen with traces of heavier elements, oxygen, carbon, nitrogen, silicon, iron, the products of previous generations of stars that had lived, died, and scattered their enriched material into space. Something disturbed this cloud, perhaps a nearby supernova. A massive star exploding at the end of its life sent a shockwave rippling through space. Perhaps the cloud simply accumulated enough mass that its own gravity began to dominate. Whatever the trigger, a region of the cloud began to collapse, to fall inward under its own gravity, growing denser, warmer, spinning faster as it contracted. This is how stars are born. As the cloud collapsed, most of its mass fell toward the center, heating up through compression, eventually becoming so hot and dense that nuclear fusion ignited. The sun was born, a new star blazing to life, beginning its long career of converting hydrogen into helium, releasing energy that would warm the inner solar system for billions of years. But not all the material fell into the sun. Some remained in orbit, forming a disk around the young star. The protoplanetary disk, a swirling plane of gas and dust from which planets would eventually form. This disk was vast, extending billions of kilometers from the sun, and it was differentiated by temperature. Close to the sun, where temperatures were high, only materials with high melting points could condense. Metals like iron and nickel, minerals like silicate, volatile materials, water, methane, ammonia, remained gaseous, couldn't form solids, were blown outward by radiation pressure and the solar wind. Farther from the sun, beyond what's called the frost line. Temperatures were low enough that volatile materials could freeze into ice. Here, the building blocks of planets included not just rock and metal, but also vast quantities of ice, making planet formation more efficient because there was simply more material available. This temperature gradient is why the inner planets, Mercury, Venus, Earth, Mars, are rocky, composed primarily of silicates and metal, while the outer planets, Jupiter, Saturn, Uranus, Neptune, are gas and ice giant, massive worlds with thick atmospheres of hydrogen and helium surrounding cores of rock and ice. But planets didn't form instantaneous. The process took time, millions of years, and it was gradual, chaotic, violent. It began with dust. Tiny particles in the protoplanetary disk, micrometers to millimeters in size, collided as they orbited the sun. Sometimes these collisions were gentle enough that the particles stuck together through van der Waals forces, weak molecular attractions that could bind small grains into slightly larger clumps. These clumps grew, attracting more dust, building up through countless collisions. As they grew, their gravity increased, allowing them to attract material not just through direct collision, but through gravitational attraction. The process accelerated. Larger bodies grew faster, sweeping up material from wider regions of the disk, becoming what we call planetesimals, objects ranging from kilometers to hundreds of kilometers in diameter. The protoplanetary disk became filled with these planetesimals, thousands or millions of them, all orbiting the sun, all occasionally colliding, all participating in a grand cosmic construction project. Some collisions were gentle enough that planetesimals merged, building larger bodies. Other collisions were violent, shattering one or both objects, sending fragments flying, sometimes allowing those fragments to reaccumulate later. Over millions of years, the largest planetesimals, those that got lucky early, that had slightly more mass or happened to be in regions with more material, grew into planetary embryos, objects the size of Mars or Mercury, massive enough that their gravity dominated large regions of the disk. These embryos continued to grow, but now through more violent collisions, through impacts with other large bodies that could partially or completely melt both objects, that could reshape surfaces, blow off atmospheres, fundamentally alter the structure of the growing world. The inner solar system had perhaps dozens of these planetary embryos, all in slightly different orbits, all growing, all occasionally interacting gravitationally, all occasionally colliding. It was a crowded, chaotic environment, a shooting gallery where massive impacts were not rare catastrophes, but regular occurrences, part of the normal process of planet formation. Earth was one of these growing embryos. About 4.5 billion years ago, roughly 100 million years after the solar system began forming, Earth had accumulated much of its current mass, grown to perhaps 90% of its final size through countless impacts with smaller planetesimals. It was not yet the Earth we know. Its surface was molten or semi-molten, kept liquid by the heat of impact, by the energy of gravitational contraction, by the decay of radioactive elements in its interior. It had no oceans, no continents, no atmosphere as we'd recognize it, perhaps some gases temporarily captured from impact or degassed from the interior, but nothing stable, nothing permanent. Earth was still growing, still sweeping up material from its orbital region, still experiencing impact, and somewhere else in the inner solar system, another planetary embryo was also growing, also evolving, also moving on an orbit that, through gravitational interactions with other bodies, through the chaotic dynamics of many objects pulling on each other, was gradually changing, slowly converging toward Earth's orbit. We call this body Theia, named after the Greek Titaness, who was the mother of Selene, the goddess of the moon. The name is fitting, poetic even, because Theia would indeed give birth to the moon, though not through any mythological process, but through the most violent collision imaginable. We don't know much about Theia directly. It no longer exists as a separate body. Its remnants are scattered. Some became part of Earth, some became part of the moon. Some were thrown into space and eventually swept up by the sun or other planets or ejected from the solar system entirely. We reconstruct what Theia was like through computer simulation, through analysis of lunar samples, through comparison with meteorites and other solar system bodies. Theia was probably similar in size to Mars, perhaps 4,000 to 6,000 kilometers in diameter, roughly half Earth's diameter. This makes Theia large, a substantial planetary embryo, a world in its own right, not some minor asteroid or comet, but a genuine protoplanet that might, in a different timeline, have become one of the terrestrial planets we know today. Theia had a differentiated structure, almost certainly. This means its interior had separated into layers, a dense iron-nickel core at the center, surrounded by a silicate mantle of lighter rock. This differentiation occurs naturally in large bodies because denser materials sink while lighter materials rise, a process driven by gravity and facilitated by heat that makes the interior soft enough for materials to flow. Theia's surface would have been molten or semi-molten, like Earth, still hot from formation, still experiencing impact. It probably had no atmosphere to speak of, or only a thin temporary envelope of gases that would have been stripped away by the solar wind or lost to space through the body's relatively weak gravity. It was not a habitable world, not a place where life could exist. It was a ball of hot rock and metal, still in the process of becoming a planet, still growing, still evolving, and it was on a collision course with Earth, not immediately. The collision didn't happen right away. Theia and Earth orbited the sun for perhaps millions of years in similar but not identical orbit, occasionally passing relatively close, their orbits gradually being modified by gravitational interactions with each other and with other planetary embryos still present in the inner solar system. Over time, through a process that was essentially random, essentially chaotic, the orbits converged. Perhaps a close encounter with another embryo changed Theia's orbit slightly. Perhaps mutual gravitational tugs between Earth and Theia gradually altered their path. Perhaps it was simply the cumulative effect of many small influences, each insignificant on its own, but adding up over time to a significant chain. Whatever the specific sequence of events, the result was inevitable once the orbits came close enough. Earth's gravity began to dominate Theia's motion. Theia was captured, pulled into an orbit that would intersect with Earth's. The distance closed, millions of kilometers, then hundreds of thousands, then thousands. Theia accelerated as it fell toward Earth, gaining speed from Earth's gravitational pull, moving faster and faster. From Earth's surface, if there had been anyone there to observe, Theia would have appeared in the sky, growing larger day by day. A second sun, perhaps, a bright object moving against the background of stars. Over days or weeks, it would have grown from a point of light to a visible disk, to a massive sphere filling more and more of the sky, its cratered surface becoming visible, perhaps glowing dully red from its own internal heat. The impact, when it came, was not head-on. This is crucial to understanding what happened, why the collision produced a moon rather than simply destroying both worlds. If Theia had struck Earth directly, at a perpendicular angle, the collision would have been even more catastrophic. Both worlds would have been completely disrupted, shattered into fragments, possibly destroying both entirely, or leaving only a severely damaged Earth struggling to reaccumulate. Instead, Theia struck Earth at an angle, a glancing blow that was still devastating, but that allowed some of Earth's structure to remain intact. The exact angle is debated. Simulations suggest something around 30 to 45 degrees from horizontal, but the key point is that it was oblique, not perpendicular. Imagine, as best you can, that moment of impact. Theia, moving at perhaps 4 to 5 kilometers per second, about 15,000 kilometers per hour, strikes Earth's surface. The first point of contact experiences pressures and temperatures beyond imagination. Rock behaves not as solid, but as fluid, as gas almost. Shockwaves propagate through both bodies at speeds of several kilometers per second, compressing material ahead of them, releasing that compression behind them in waves of incredible violence. The collision lasts hours, not minutes, because Theia is large and the impact is grazing. As Theia's leading edge strikes Earth, the trailing edge is still approaching, still tens of thousands of kilometers away. Material from both bodies is thrown into space at velocities exceeding escape velocity. Other material is heated to tens of thousands of degrees, vaporized, turned into a plasma of ionized atoms glowing brilliant white or blue. The energy release is staggering, difficult to comprehend. The impact released energy equivalent to billions or trillions of nuclear weapons, energy comparable to the output of the sun for days or weeks. Enough energy to melt both worlds, to vaporize portions of their surfaces, to reshape continents if continents had existed, which they didn't, to completely transform both bodies. Earth's surface, where the impact occurred, was obliterated. Rock turned to liquid, then to vapor. A crater formed, not a neat circular depression, but an enormous gash, a wound stretching thousands of kilometers, deep enough to expose Earth's mantle, hot enough to melt iron. The shockwave propagated through Earth's interior, focusing on the opposite side of the planet, in an effect called an antipodal effect, creating disruption and heating even on the far side from impact. Theia fared worse. Being smaller, with less structural integrity, with less mass to hold it together, Theia was disrupted almost completely. Its core, the dense iron-nickel center, probably remained somewhat intact, a massive projectile that plowed through Earth's mantle and either merged with Earth's core or perhaps remained distinct for some time as a separate blob of metal within Earth's interior, before eventually mixing. Theia's mantle, the silicate rock surrounding its core, was largely destroyed as a coherent structure. Some merged with Earth, adding to Earth's mass, heating Earth's mantle, mixing with Earth's own silicate rock. But much was thrown into space, ejected by the violence of the collision, sent flying outward in all directions. Earth's rotation was affected. Before the impact, Earth was probably rotating relatively slowly, its day perhaps 6 to 10 hours long. The impact, because it was angled, imparted angular momentum to Earth, causing it to spin faster. After the collision, Earth's day was perhaps 5 hours long, the planet rotating rapidly on its axis, bulging at the equator from centrifugal force. The impact also tilted Earth's axis. Earth's axial tilt, the angle between its rotation axis and the plane of its orbit around the Sun, is currently about 23.5 degrees. This tilt is responsible for season, for the variation in sunlight at different latitudes throughout the year. Before the Theia impact, Earth's tilt might have been different, perhaps smaller. The collision changed it, leaving Earth with the tilt it has maintained for billions of years. But the most important consequence of the impact, the one we're most concerned with, was the debris. Enormous amounts of material, rock, metal, vapor, were thrown into space by the collision. Some of this material was ejected at velocities exceeding Earth's escape velocity, about 11 kilometers per second, and was lost to space forever, eventually falling into the Sun or being swept up by other planets or wandering through the solar system as small asteroids. But much of the ejected material, perhaps more than half, was thrown into space at velocities below escape velocity. This material went into orbit around Earth, forming a ring of debris encircling the planet. This ring was not like Saturn's ring, not thin and composed small particles. This was a massive structure, containing perhaps the mass of a small moon, or even a large moon, extending tens of thousands of kilometers from Earth, composed of a mixture of solid rock, molten droplet, and vaporized material, condensing into liquid and solid particles. This debris ring was extraordinarily hot. Material ejected by the impact was heated to thousands of degrees, and even as it cooled in space, radiating heat to the vacuum, it remained molten or semi-molten for days, weeks, perhaps longer. The debris glowed red and orange and white, a spectacular sight if there had been anyone to observe it. Earth surrounded by a glowing ring of molten rock, brighter than any ring system we see in the solar system today. Imagine looking at Earth from space in the hours and days after the impact. Earth itself is unrecognizable. Its surface is largely molten, glowing red with heat, covered by a magma ocean hundreds of kilometers deep. No solid crust yet, no continents, no oceans, just liquid rock slowly convecting, slowly cooling, gradually solidifying from the top down as heat radiates to space. And around this molten Earth, the debris ring, a band of glowing material encircling the planet's equator, perhaps several Earth radii wide, shimmering with heat, slowly evolving. Within this ring, physics is at work. The solid particles and molten droplets are colliding, sometimes gently enough to stick together, sometimes violently enough to shatter or splash apart. Gravity is pulling material together, trying to form larger bodies, but the ring is close to Earth, within what's called the Roche limit, a distance inside which tidal forces from Earth's gravity are stronger than the self-gravity of any object trying to form. The Roche limit is important. For a moon of similar density to Earth, the Roche limit is about 2.5 Earth radii, about 16,000 kilometers from Earth's center. Inside this distance, Earth's tidal forces, the difference in gravitational pull on the near and far sides of an object, are strong enough to prevent material from coalescing into a single large body. Objects trying to form are pulled apart by tides before they can grow large. But outside the Roche limit, beyond about 16,000 kilometers from Earth's center, material can accumulate. Here, self-gravity dominates over tidal forces. Particles can stick together, can merge, can build larger and larger bodies without being torn apart. The debris ring probably extended both inside and outside the Roche limit. Material inside the limit couldn't form a moon, but but it could interact, could collide, could exchange momentum. Through these interactions, material gradually moved, spreading out within the ring. Some material moved inward, eventually falling back to Earth, raining down on the still molten surface. Other material moved outward, beyond the Roche limit, where it could begin to accumulate. This process took time. The ring didn't instantly form a moon. Instead, over weeks to months, possibly years, material in the outer portions of the ring began to clump. Larger bodies grew, attracting more debris, growing faster through gravitational attraction. Multiple bodies probably formed initially, perhaps dozens or hundreds of moon-sized objects, each growing in its own orbital zone within the ring. These proto-moons interacted gravitationally. Their orbits weren't perfectly circular, weren't perfectly stable. They perturbed each other, tugged on each other, sometimes came close enough to collide and merge. Over time, through this process of gravitational interaction and collision, the multiple proto-moons consolidated into fewer, larger objects. Eventually, one object became dominant, sweeping up most of the material in the ring, growing into the moon. Other smaller bodies might have remained for a time, small moons orbiting Earth alongside the large moon, but these were probably short-lived. They either collided with the moon, adding their mass to it, or were ejected from Earth orbit through gravitational interaction, or fell back to Earth. The result, perhaps 10,000 to 100,000 years after the impact, a blink in geological time, was a single, large moon orbiting Earth. This moon was not yet the moon we know. It was much closer to Earth, perhaps only 25,000 to 30,000 kilometers away, compared to the current 384,000 kilometers. It was still hot, still partially molten from the heat of the impact and from the energy of its own formation. Its surface was covered by a magma ocean, similar to Earth, slowly cooling, slowly solidifying. But it was recognizably the moon. It had roughly the mass it has today, about 1.2% of Earth's mass. It had a similar composition, largely silicate rock, with a small iron core. It orbited Earth in the plane of Earth's equator, because it formed from material ejected, mostly along Earth's equator, by the glancing impact. And it was tidally locked, or quickly becoming so, meaning it always showed the same face to Earth, its rotation synchronized with its orbit by Earth's strong tidal forces. From Earth's surface, if the surface had been solid enough to stand on, which it wasn't yet, the moon would have been spectacular, 15 times larger in apparent diameter than the moon appears today, dominating the sky, filling perhaps 30 degrees of arc from edge to edge, showing incredible detail, lava plains, impact craters, mountain ranges if any had formed yet, all visible to the naked eye in incredible resolution. And it moved quickly across the sky because it was so close, and because Earth's day was so short, the moon would rise and set multiple times per day, racing across the heavens in hours. This early moon also raised enormous tides on Earth. Tides are caused by the differential gravitational pull of the moon on different parts of Earth. The side facing the moon is pulled more strongly than Earth's center, which is pulled more strongly than the far side, creating bulges of material on both sides. When those bulges are in the ocean, we get water tide. When Earth's crust was still partially molten, the tides were much larger, raising bulges of molten rock hundreds of meters high, maybe more. These tides dissipated energy through friction, through the movement of material against itself. This energy had to come from somewhere, and it came from the Earth-Moon system's orbital energy. The result was that the moon's orbit gradually expanded. The moon slowly moved away from Earth, and Earth's rotation gradually slowed. Earth's day lengthened. This process continues today, though at a much slower rate. The moon is still receding from Earth at about 3.8 centimeters per year, and Earth's day is still lengthening at about 2 milliseconds per century. But in the early days, when the moon was close, and Earth was rotating rapidly, and the tides were enormous, the recession was much faster. The moon moved outward quickly, reaching perhaps 60,000 kilometers within the first million years, 100,000 kilometers within 10 million years, gradually slowing its outward migration as the tidal forces weakened with distance. By about 4.4 billion years ago, roughly 100 million years after the impact, Earth and Moon had largely solidified. Earth's magma ocean had cooled enough to form a solid crust, though the interior remained hot. partially molten, vigorously convecting. The moon's surface had also solidified, forming the anorthosite crust that characterizes the lunar highlands today. Both bodies still experienced impact. The solar system was still full of debris, planetesimals that hadn't been swept up yet, but the major construction phase was over. Earth and moon existed in recognizable form. How do we know all this? How do we know that the moon formed from a giant impact 4.5 billion years ago? We weren't there to observe it. We have no direct records from that. Earth's rocks from that era have been destroyed by geological process, plate tectonics, erosion, metamorphism. Even the oldest Earth rock are only about 4 billion years old, post-dating the impact by 500 million years. The evidence is indirect but compelling, coming from multiple lines of reasoning that all point to the same conclusion. First, the moon's composition. The moon is similar to Earth in many ways, but different in crucial detail. Both are made primarily of silicate rock, minerals containing silicon and oxygen, but the relative abundances of different elements differ. The moon is depleted in volatile elements, those that vaporize easily at low temperature, like water, sodium, potassium. The moon is also depleted in iron compared to Earth. Earth is about 32% iron by mass, mostly concentrated in its core. The moon is only about 5 to 10% iron with a very small core. These compositional features make sense if the moon formed from material that was heated to very high temperature, hot enough to vaporize volatile elements and allow them to escape to space, but not hot enough or not under the right condition to retain iron. A giant impact provides exactly these conditions. The material ejected into the debris ring would have been heated to thousands of degrees, vaporizing water and other volatile. The iron, being denser, would have largely stayed with Earth or Theia, sinking toward the cores of both bodies, not being preferentially ejected into the ring. Second, isotopic similarities. Different elements come in different isotopes, variants with the same number of protons, but different numbers of neutrons. The relative abundances of isotopes vary slightly between different bodies in the solar system, a result of different formation conditions, different source materials, different processes. Earth and moon rocks have almost identical isotopic compositions for many elements: oxygen, tungsten, titanium, chromium. This similarity suggests that Earth and moon formed from the same material or from very similar material. If the moon had formed elsewhere in the solar system and been captured by Earth's gravity, we'd expect its isotopic composition to be different from Earth's, because different regions of the solar system have measurably different isotopic signatures. If the moon had formed alongside Earth from the same disk of material, but as a separate body, we might still expect some differences due to different conditions in different parts of Earth's orbit. But the near-identical isotopic composition suggests that the moon formed from Earth material, or from material that mixed thoroughly with Earth's material. A giant impact does this. Material from both Earth and Theia is heated, vaporized, mixed in the debris cloud, then condenses to form the moon. The isotopic homogeneity results from this mixing. Interestingly, the isotopic similarity also constrained models of the impact. Early simulations suggested that most of the moon's material came from Theia, not Earth. But if Theia had a different isotopic composition from Earth, which most bodies in the solar system do, then the moon should have Theia's isotopic signature, not Earth. The fact that the moon's composition matches Earth so closely suggested either that Theia happened to have the same isotopic composition as Earth, possible but unlikely, or that more Earth material ended up in the moon than early models predicted. More recent simulations, using supercomputers and more sophisticated physics, have found scenarios where the moon is composed more of Earth material than Theia material, or where the impact mixed material so thoroughly that the resulting moon has an intermediate composition indistinguishable from Earth's. These newer models better match the isotopic evidence. Third, Earth's angular momentum. The Earth-Moon system has unusually high angular momentum. The combined rotational and orbital motion is greater than we'd expect for Earth alone. Where did this extra angular momentum come from? A giant impact delivered at an angle can impart angular momentum to the system, explaining why Earth spins relatively quickly, even though it's slower now than immediately after impact, and why the moon orbits relatively far from Earth. Fourth, Earth's axial tilt. As mentioned, Earth's axis is tilted about 23.5 degrees from perpendicular to its orbital plane. This tilt is larger than for most planets and is stable over billions of years, maintained by the moon's gravitational influence. A giant impact could have created this tilt, setting Earth spinning at an angle that has persisted ever since. Fifth, the lack of other plausible scenarios. Before the giant impact hypothesis became widely accepted in the 1980s and 1990s, there were three main theories for the moon's origin. Fission theory: the moon split off from Earth while Earth was rotating rapidly, perhaps thrown off by centrifugal force. This was Darwin's idea. Charles Darwin's son George, who was an astronomer. The problem is that Earth would have had to be rotating impossibly fast to throw off the moon's mass, and there's no mechanism to make Earth spin that fast. Capture theory: the moon formed elsewhere in the solar system and was captured by Earth's gravity when it passed close by. The problem is that capturing a body as large as the moon is extremely difficult. Most close encounters would result in either collision or the smaller body being flung away. The energy involved in capture would probably cause so much tidal heating that both bodies would melt, and there's no evidence for this. Also, as mentioned, capture doesn't explain the isotopic similarities between Earth and Moon. Co-formation theory: Earth and Moon formed together from the same disk of material as a binary planet system. The problem is that this doesn't explain the moon's compositional oddities: its low iron content, its depletion in volatiles. If Earth and Moon formed together, they should have similar iron abundances. None of these scenarios adequately explained the evidence, but a giant impact could. It explained the moon's composition, the isotopic similarity, the angular momentum, the tilt, everything. When researchers first seriously modeled giant impacts in the 1970s and 1980s using early computer simulation, they found that such impacts could produce debris rings that would coalesce into moons with properties matching our moon. The hypothesis gained credibility through the 1980s and 1990s as more detailed simulations were run, as lunar samples from the Apollo missions were analyzed in more detail, as our understanding of planetary formation improved. Today, the giant impact hypothesis is the standard model, accepted by almost all planetary scientists, though details are still being refined. Let's talk about those lunar samples, because they provide crucial evidence. Between 1969 and 1972, the Apollo missions brought back 382 kilograms of lunar rock and soil from 6 different landing sites. These samples were analyzed extensively and continue to be analyzed today using increasingly sophisticated techniques. The Apollo samples confirmed that the moon's surface is ancient. The oldest lunar rocks are about 4.5 billion years old, dating to shortly after the moon's formation. These rocks are anorthosite, light-colored igneous. Rocks rich in the mineral plagioclase feldspar. They form the lunar highlands, the bright regions visible from Earth. The anorthosites tell us about the moon's early history. They formed as the lunar magma ocean cooled. Plagioclase, being less dense than the liquid magma, floated to the surface, accumulating in thick layers that solidified into the anorthosite crust. This process is called fractional crystallization, and it requires a global magma ocean, consistent with the moon forming hot from an impact. The darker regions of the moon, the Maria, Latin for seas, though they contain no water, are younger, dating to between 3.1 and 3.9 billion years ago. The Maria are basalts, volcanic rocks that formed when the moon's interior partially melted and lava flowed onto the surface, filling large impact basins. The Maria tell us that the moon's interior remained hot for hundreds of millions of years after formation, hot enough to generate volcanism, consistent with the moon forming from hot impact debris. The Apollo samples also showed that the moon is bone dry. No water, no hydrated minerals, no water-bearing compound. The hydrogen that would be in water or other volatile compounds is simply absent. This is consistent with the moon forming from material that was heated to very high temperatures, vaporizing water and allowing it to escape to space. Interestingly, more recent discoveries, using orbital spacecraft with sensitive instruments, have detected traces of water ice in permanently shadowed craters near the lunar poles. This water is not native to the moon's formation, but was delivered later by comet or water-bearing asteroids impacting the surface. The ice survived only in cold traps, craters that never see sunlight, where temperatures are cold enough to preserve ice for billions of years. The Apollo samples also provided precise measurements of isotopic composition. As mentioned, the oxygen isotopes, the titanium isotopes, the chromium isotopes in lunar rocks are almost identical to Earth's within measurement error. This was surprising when first discovered, because other solar system bodies have measurably different isotopic signatures. It implied that the Moon and Earth are made of the same material, supporting the giant impact hypothesis. One isotope in particular, tungsten 182, provided crucial timing information. Tungsten-182 is produced by the radioactive decay of hafnium-182, which has a half-life of only 9 million years. This means that hafnium-182 existed in the early solar system, but decayed away quickly. If the Moon formed early, while hafnium-182 still existed, the tungsten isotope ratio in lunar rocks would reflect this. If the Moon formed later, after hafnium-182 had decayed, the ratio would be different. Measurements of tungsten isotopes in lunar samples indicated that the Moon formed within about 100 million years after the solar system began forming, consistent with the timing of the giant impact. This timing also makes sense in the context of planet formation. 4.5 billion years ago is about when the large planetary embryos like Earth and Theia would have been nearing their final sizes, when giant collisions between embryos would have been occurring. Beyond lunar samples, we have evidence from computer simulations. Starting in the 1970s and accelerating with the availability of powerful computers, researchers have modeled giant impacts using computational techniques called smooth particle hydrodynamic, SPH, or more recently, grid-based methods. These simulations model Earth and Theia as collections of particles or cells, each representing a chunk of rock or metal with specific properties: density, temperature, pressure. The simulation calculates gravitational forces between all particles, calculates how they move and collide, calculates how pressure and temperature change during the impact, tracks how material is heated, melted, vaporized, and ejected into space. Early simulations were crude, with limited resolution and simplified physics, but they showed that a giant impact could produce a debris disk that would coalesce into a moon. As computers became more powerful and models more sophisticated, simulations could include more realistic physics, equation of state models that accurately describe how rock behaves under extreme pressure, models of vaporization and condensation, better gravity calculation, higher resolution. Modern simulations running on supercomputers with millions of particles or cells can model the impact in extraordinary detail. They show the shockwave propagating through both bodies, show material being ejected at different velocities, show the debris disk forming and evolving, show proto-moons accumulating from the debris. Different simulations test different impact parameters, different sizes for Theia, different impact velocities, different impact angles, to see which scenarios produce results matching what we observe about the Moon. The simulations have revealed that the details matter. The Moon we see today, its size, composition, orbit, is best reproduced by a relatively narrow range of impact scenarios. Too small an impactor, and there's not enough material to make the Moon. Too large, and Earth might be destroyed entirely. Too fast an impact, and too much material is lost to space. Too slow, and the debris doesn't reach orbit. Too direct an angle, and the impact is too destructive. Too shallow, and the bodies might not merge properly. The Goldilocks scenario that works best has Theia about Mars size, impacting at 4 to 5 kilometers per second at an angle of 30 and 45 degrees. This produces enough ejected material to form the Moon, leaves Earth largely intact though severely damaged, imparts the right amount of angular momentum, and creates the compositional features we observe. Recent simulations have explored even more extreme scenarios. Some researchers have proposed that Theia was much larger than Mars, possibly as large as Earth itself, and that the impact was even more violent than traditionally thought. These synestia models suggest that the impact created a synestia, a new type of planetary structure, a donut-shaped mass of vaporized rock surrounding Earth, extending tens of thousands of kilometers into space, spinning rapidly. According to these models, both Earth and Moon condensed from this synestia, which would explain their similar isotopic compositions even better than traditional models. Other researchers have proposed multiple impacts, not just one. Perhaps Theia hit Earth, then a second large body hit later, or perhaps several medium-sized bodies hit in succession. These scenarios might also explain some of the Moon's features, though they're generally considered less likely than a single large impact, because multiple giant impacts would be less probable statistically. The point is that while the giant impact hypothesis is well established, the details are still being worked out. Science is iterative, constantly refining our understanding as new evidence emerges, as new techniques become available, as more sophisticated models are developed. The basic picture that the Moon formed from debris created by a Mars-sized impactor striking Earth 4.5 billion years ago is very solid. The specifics, exactly how large the impactor was, exactly what angle, exactly how the debris evolved into the moon, are still areas of active research. Let's return to the story, to what happened after the moon formed, after it coalesced from the debris ring, after it began its existence as Earth's companion. The early moon was a very different place from the moon we see today. As mentioned, the moon was close to Earth, perhaps 25,000, 30,000 kilometers away, and it was hot, still partially molten from its formation. Its surface was covered by a magma ocean, liquid rock hundreds of kilometers deep, glowing red with heat. This magma ocean cooled over time, radiating heat to space, solidifying from the top down. As the magma cooled, minerals began to crystallize out of the liquid, forming solid crystals that either floated or sank depending on their density. Dense minerals like olivine and pyroxene, rich in iron and magnesium, sank toward the bottom, forming the moon's mantle. Less dense minerals like plagioclase feldspar floated to the top, accumulating in thick layers that would become the lunar crust. This process of fractional crystallization took perhaps 10 million to 100 million years. Eventually, the entire magma ocean solidified, leaving the moon with a layered structure, a small iron core at the center, a thick mantle of dense silicate rock, and a lighter crust of anorthosite floating on top. This is the basic structure the moon has retained to the present, though modified by subsequent impacts and volcanic activity. The anorthosite crust is thick, perhaps 35 to 40 kilometers on average, thicker than Earth's crust. It's also ancient, dating to this early period of crystallization. When we look at the bright lunar highlands through a telescope or with the naked eye, we're seeing this ancient crust formed within the first 100 million years of the moon's existence. But the moon's early history wasn't peaceful after the magma ocean solidified. The solar system was still full of debris, planetesimals, asteroids, comets, left over from planet formation. These objects continued to bombard the inner planets and their moons for hundreds of millions of years in what's called the late heavy bombardment, though recent research questions whether there was a distinct late bombardment or just a gradual tail-off of impacts from the formation era. Regardless of the exact timing and intensity, the moon was heavily impacted. Being smaller than Earth, with weaker gravity, the moon couldn't capture much of an atmosphere even if one tried to form, so there was no protection from impact. And having no plate tectonic, no geological activity to resurface and erase old craters, the moon preserved a record of these ancient impacts. The largest impacts created enormous basins, circular depressions, hundreds or thousands of kilometers in diameter. The Imbrium Basin, Mare Serenitatis, Mare Tranquillitatis, the Crisium Basin, these are all impact structures, scars from enormous collisions that occurred between about 3.9 and 4.1 billion years ago. The largest, the South Pole Aitken Basin, is over 2,000 kilometers in diameter, one of the largest impact structures in the solar system. These giant impacts fractured the lunar crust, creating zones of weakness through which molten rock from the interior could later reach the surface. Between about 3.9 and 3.1 billion years ago, the moon's interior was still hot enough to be partially molten, and magma rose through these fractures, erupting onto the surface, flowing into the low-lying impact basin, filling them with layers of basalt, sometimes kilometers thick. These basalt flows are the lunar maria, the dark patches we see on the moon. They're younger than the bright highland, dating to this period of volcanic activity, and they're compositionally distinct, richer in iron, which makes them darker. The maria cover about 16% of the moon's surface, mostly on the near side, the side facing Earth, because the crust is thinner on the near side, making it easier for magma to reach the surface. Why is the crust thinner on the near side? This is another mystery, still not fully resolved. It might be related to Earth's tidal force, which would have been stronger on the near side, perhaps affecting how the magma ocean crystallized. Or it might be related to a large impact that preferentially thinned the near side crust. Or it might simply be chance, a consequence of how crystallization proceeded in the cooling magma ocean. The maria are the last major geological activity on the moon. After about 3.1 billion years ago, the moon's interior cooled enough that volcanic activity ceased. Since then, the moon has been essentially geologically dead, with only impacts modifying its surface. Craters continue to accumulate, but at a much slower rate than in the early solar system, because most of the debris has been cleaned up, swept up by planets, or ejected from the inner solar system. The moon we see today is therefore ancient, a preserved snapshot of what planets looked like billions of years ago. Earth's surface has been completely reworked by plate tectonics, erosion, and biological activity. No Earth rocks survive from the first 500 million years of Earth's history, but the Moon preserves a record of that time, frozen in its ancient crust, visible in its craters, accessible if we're willing to go there and study it. This is one reason why studying the Moon is scientifically valuable. It's not just interesting in its own right, but is a window into early solar system history, a place where we can see and touch rocks that date to the period of planet formation, rocks that can tell us about conditions in the early solar system, about the bombardment history, about how planets evolve. The Apollo astronauts understood this. When they walked on the Moon, collected rocks, took photographs, set up experiments, they were doing science of extraordinary importance. The samples they brought back have been studied for over 50 years and continue to yield new insights. Some samples have never been opened, preserved for future analysis with techniques that don't exist yet. Let's think about the Moon's influence on Earth, because the Moon isn't just a passive companion, but has played crucial roles in shaping Earth's environment, Earth's climate, possibly even the evolution of life. The most obvious influence is tide. The Moon's gravity pulls on Earth, creating bulges in the ocean, high tides on the side facing the Moon, and on the opposite side, low tides in between. As Earth rotates, different locations move through these bulges, experiencing high and low tides throughout the day. Tides affect coastal ecosystems profoundly. The intertidal zone, the region between high and low tide marks, is a unique environment, sometimes submerged, sometimes exposed, home to specialized organisms adapted to these changing conditions. Tides drive nutrients, mix water, affect sediment transport, influence where organisms can live. Early in Earth's history, when the Moon was closer and tides were much larger, the intertidal zone would have been more extensive and more dynamic. Some researchers have proposed that this environment, pools of water regularly filled and drained by tides, concentrating chemicals, providing cycles of wet and dry, might have been favorable for the origin of life, for the chemistry that led from non-living molecules to living systems. This is speculative, but it's an interesting idea. Life requires concentration. Dilute solutions don't react efficiently. Tidal pools, evaporating between tides, would naturally concentrate molecules. Life requires cycles, wet-dry. Cycles can drive polymerization reactions, building longer molecules from shorter precursors. Tidal pools provide these cycles naturally. Life requires energy. Tidal energy, though small per event, is reliable, cyclic, persistent. Perhaps the Moon's tides helped life get started. Once life existed, the Moon's influence continued through its effect on Earth's axial tilt. As mentioned, Earth's axis is tilted 23.5 degrees, causing seasons. Summer, when your hemisphere tilts toward the sun. Winter, when it tilts away. These seasons have been crucial for life, driving annual cycles of temperature, rainfall, plant growth, animal migration. But Earth's tilt isn't perfectly stable. Over tens of thousands of years, it varies slightly, oscillating between about 22 and 25 degrees in a cycle called obliquity variation. This variation is small and doesn't dramatically affect climate over short timescales, but without the Moon, Earth's tilt would be much less stable. Computer simulations show that without the Moon's stabilizing influence, Earth's axial tilt could vary chaotically, swinging through a huge range from nearly 0 degrees, no tilt, no season, to 85 degrees or more, extreme tilt, extreme season. Mars, which has small moons that don't provide stabilization, shows this behavior. Mars's tilt has varied from 15 to 35 degrees, or possibly more over millions of years, causing dramatic climate swings. If Earth's tilt varied chaotically, climate would be unpredictable over millions of years. Sometimes Earth would have no season, with sunlight always hitting the equator most directly. Sometimes Earth would have extreme seasons, with poles alternately pointing nearly at the sun. These swings would stress ecosystems, making long-term evolutionary adaptation difficult. The Moon prevents this. Its gravity exerts a torque on Earth's equatorial bulge, maintaining the tilt within a narrow range. This stability has persisted for billions of years, providing a consistent climate framework within which life could evolve, adapt, diversify. Without the Moon, life might still exist on Earth, but it might be less diverse, less complex, less able to adapt to the unpredictable climate swing. This is called the rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee. They argued that complex life might be rare in the universe, not because life itself is rare, but because the conditions for complex life to evolve are stringent. Among those conditions, they included having a large moon to stabilize axial tilt, to provide stable seasons over billions of years. Not everyone agrees with the rare Earth hypothesis. Critics point out that life is adaptable, that organisms might cope with variable tilt through migration, hibernation, rapid evolution. Mars might have had life early in its history, despite its tilt variation, and we don't know how common large moons are around terrestrial planets. Earth might be unusual, or large moons might be common products of giant impacts during planet formation. But whether or not the moon was necessary for life, it certainly influenced Earth's history. The moon affects ocean tide, which affect coastal environment. The moon stabilizes Earth's tilt, which affects climate stability. The moon slows Earth's rotation through tidal friction, which lengthened the day from 5 hours after the impact to 24 hours today, giving life more time to photosynthesize during daylight, more time to rest during night. The moon also affects human culture profoundly. Every culture on Earth has stories about the moon, has observed its phases, has used it to track time. The lunar cycle, 29.5 days from new moon to new moon, is the origin of the month, a natural calendar unit, observable without instrument. Many ancient calendars were lunar, tracking months as lunar cycles, though most modern calendars are solar, based on Earth's orbit around the sun. The moon has inspired art, poetry, music, mythology. It's been a goddess, a god, a clock, a calendar, a source of light and darkness, a symbol of change and constancy, of romance and madness. Lunar eclipses, when Earth's shadow falls on the moon, have been seen as omen. Solar eclipses, when the moon blocks the sun, have terrified and awed observers. It's a remarkable coincidence, perhaps literally a coincidence, or perhaps a consequence of tidal evolution, that the moon's apparent size in our sky is almost exactly the same as the sun. The moon is 400 times smaller than the sun, but also 400 times closer, so they appear the same size. This makes solar eclipses spectacular, with the moon just barely covering the sun's disk, allowing the sun's corona to be visible. This coincidence won't last forever. As the moon continues to recede, it will appear smaller in the sky. Already, some solar eclipses are annular rather than total, with the moon not quite large enough to cover the sun completely, leaving a ring of sunlight visible around the moon's silhouette. In the distant future, hundreds of millions of years from now, all solar eclipses will be annular, and total solar eclipses will be impossible because the moon will be too far away, too small in apparent size. Similarly, the moon's recession means tides will weaken over time. Earth's rotation will continue to slow. The day will continue to lengthen, eventually reaching an equilibrium where Earth's day equals the moon's orbital period. At that point, Earth will be tidally locked to the moon, just as the moon is already tidally locked to Earth. The same side of Earth will always face the moon, and the moon will hang motionless in the sky from one hemisphere, never visible from the other. This equilibrium is billions of years away, far enough in the future that the sun will have evolved off the main sequence, expanded into a red giant, possibly engulfed Earth and moon entirely. So we don't need to worry about it practically. But it's interesting to contemplate, to realize that the Earth-Moon system is still evolving, still changing, that the relationship between the two bodies is dynamic, not static. Let's talk about the moon's interior, about what we know of its structure and composition, because this too provides clues about its origin. Unlike Earth, which has been studied by seismometers at thousands of locations, providing detailed maps of its interior, the moon has been studied by only a handful of seismometers, placed by Apollo astronauts at 4 landing sites, operating for only a few years before being shut down. Nevertheless, these seismometers detected moonquakes, lunar earthquakes, both natural ones caused by tidal stresses or impacts, and artificial ones caused by deliberately crashing spent rocket stages into the surface. By analyzing how seismic waves propagated through the moon, scientists could infer the moon's internal structure. The moon has a crust, mantle, and core, like Earth, but the proportions are different. The crust is thick, averaging 30-40 kilometers on the near side, possibly up to 60 kilometers on the far side. Beneath the crust is the mantle, extending down to about 1,400 kilometers depth. The mantle is solid or mostly solid, composed of silicate minerals, but it's not uniform. The upper mantle and lower mantle have different properties, possibly different composition. At the center is the core, much smaller than Earth's core. The moon's core is probably only about 450 kilometers in radius, containing only about 1 to 2% of the moon's mass, compared to Earth's core, which is 3,500 kilometers in radius, and contains about 32% of Earth's mass. The moon's core is probably partially molten, with a solid inner core and liquid outer core, similar to Earth but much smaller. The small size of the moon's core is consistent with the giant impact hypothesis. If the moon formed from material ejected from Earth's mantle and Theia's mantle, and if the iron cores of both bodies stayed with Earth or Theia rather than being ejected, then the moon would naturally have little iron, a small core. The moon's low density, about 3.3 grams per cubic centimeter compared to Earth's 5.5, reflects this lack of iron. The moon's small core also explains why the moon has no global magnetic field. Earth has a strong magnetic field, generated by convection in its liquid iron core, a dynamo process that converts kinetic energy into magnetic energy. The moon's core is too small to sustain such a dynamo, at least not currently. The moon does have weak localized magnetic fields in some regions, recorded in lunar rock, evidence that the moon might have had a global magnetic field early in its history, when its core was hotter and more vigorously convecting. But that field disappeared perhaps 3 to 4 billion years ago as the core cooled, and since then, the moon has been magnetically quiet. This makes the moon vulnerable to solar radiation. Charged particles from the sun that would be deflected by a magnetic field instead strike the moon's surface directly, slowly breaking down rock, creating the fine powdery regolith that covers the surface. The regolith is actually quite interesting. It's not like soil on Earth, which is composed of broken rock mixed with organic matter. Lunar regolith is purely inorganic, composed of tiny rock fragments and glass beads created by countless micrometeorite impacts. Over billions of years, impacts have pulverized the surface, mixing and churning it, creating a layer several meters thick in most places. Walking on the moon, as Apollo astronauts described, involves sinking slightly into this powder, leaving deep boot prints that will last for millions of years because there's no wind or water to erase them. The regolith sticks to everything, clinging electrostatically, a constant nuisance for equipment and spacesuits. It's also abrasive, wearing down surfaces, problematic for machinery. But the regolith is also scientifically valuable. It contains a record of the solar wind, of cosmic rays, of micrometeorite bombardment, all preserved in the grains at the microscopic level. Studying regolith samples provides information about the history of the sun, about radiation in space, about the flux of small impactors over billions of years. The moon's surface is also geographically interesting, despite its lack of current geological activity. The highlands and Maria create a stark contrast, bright and dark regions visible even with the naked eye. Some cultures see a face, the man in the moon, in this pattern. Others see a rabbit or a woman or various other figures, examples of pareidolia, the human tendency to see meaningful patterns in random configuration. The far side of the moon is strikingly different from the near side. While the near side has many large maria, dark basaltic plains filling impact basin, the far side has almost none. The far side is mostly highland, heavily cratered, brighter, older. This asymmetry is still not fully explained. It might relate to the thicker crust on the far side, making volcanic activity more difficult. It might relate to the distribution of large impact, which preferentially occurred on the near side for unknown reason. Or it might be related to tidal heating from Earth, which would have been stronger on the near side. The dichotomy wasn't fully appreciated until spacecraft began orbiting the moon and photographing the far side in the 1960s. Before then, the far side was unknown, never visible from Earth, because the moon is tidally locked, always showing the same face toward us. The Soviet Luna 3 mission in 1959 took the first photographs of the far side, revealing its different character, showing that the moon was not symmetric. Among the moon's most dramatic features are its rays, bright streaks radiating from young impact craters. These rays are composed of material ejected by the impact, thrown outward at high velocity, landing hundreds or thousands of kilometers from the crater, creating bright splashes on the darker background. The rays are bright because they're fresh, not yet darkened by space weathering, the gradual process by which solar wind and micrometeorites darken lunar surface materials. The most prominent ray crater is Tycho, a large crater in the southern highland. Tycho's rays extend across much of the near side, visible even with small telescopes or binoculars, especially around full moon when the sun illuminates the surface directly and shadows don't obscure features. Tycho is relatively young, only about 100 million years old, recent enough that its rays remain bright. Older craters lack prominent rays because the rays have been darkened by billions of years of space weathering. This allows geologists to determine relative ages of craters. Those with bright rays are younger than those without. Combined with radiometric dating of samples from known craters, this allows construction of a chronology, a timeline of lunar surface history. The moon has been visited by human beings 6 times during the Apollo missions from 1969 to 1972. 12 astronauts walked on the surface, conducted experiments, collected samples, drove rovers, planted flags, left plaques and instruments. These missions were political, driven by Cold War competition between the United States and Soviet Union. But they were also scientific triumphs, expanding human knowledge of the moon enormously. The Apollo sites are now historical landmarks, protected by international agreement, even though no law technically governs them. The footprints, the flags, likely bleached white by solar radiation, the rovers, the descent stages of the lunar modules, all remain on the surface, unchanged, exactly as the astronauts left them. In the absence of erosion, they'll last millions of years, monuments to humanity's first steps on another world. But we haven't returned since 1972. The political will and funding disappeared after Apollo. And for 50 years, no humans have left low Earth orbit. Robotic missions have continued. Orbiters, landers, rovers from NASA, ESA, China, India, Japan, Israel, others. But no people. That's changing. Multiple nations and private companies are planning crewed moon missions for the 2020s and 2030s. NASA's Artemis program aims to land astronauts on the moon's south pole, where permanently shadowed craters might contain accessible water ice. China is planning crewed missions. SpaceX is developing the Starship vehicle, partly for lunar mission. A new era of lunar exploration is beginning. The motivation is partly scientific. There's still much to learn about the moon, especially regions not visited by Apollo, but also economic and strategic. The moon might contain valuable resources: water ice that can be split into hydrogen and oxygen for rocket fuel, metals that could be mined, helium-3 that might someday fuel fusion reactors. The moon could serve as a base for deeper space exploration, a stepping stone to Mars and beyond, a place to test technologies and techniques for living off Earth. Whether this new lunar era materializes as envisioned remains to be seen. Space exploration is expensive, politically vulnerable, technically challenging, but the moon remains accessible, only 3 days away by rocket. Close enough that communication is nearly instantaneous. Close enough that rescue missions are conceivable if something goes wrong. And beyond practical considerations, the moon draws us. It's part of our sky, part of our culture, part of our history. Returning to the moon, establishing a permanent presence there, would be a symbolic achievement as well as a practical one, a statement that humanity is not confined to one world, that we can live and work beyond Earth, that our future might extend into the solar system and beyond. Let's zoom out now. Think about the moon's origin in the broader context of planet formation, because Earth and Theia's collision wasn't unique. Giant impacts were common during the late stages of terrestrial planet formation, and other planets likely experienced similar events. Mercury, the innermost planet, has an unusually large iron core, composing about 60% of its mass, far more than Earth or Venus. One explanation is that Mercury experienced a giant impact that stripped away much of its silicate mantle, leaving the iron core exposed beneath a thin shell of silicate rock. This would explain Mercury's high density and peculiar composition. Mars is smaller than we'd expect for a planet in its orbital position, leading some researchers to propose that Mars lost mass through one or more giant impacts, perhaps ejecting material that was then swept up by Earth or by Jupiter. Mars also has a stark dichotomy between its northern and southern hemispheres. The north is low and smooth, possibly once an ocean basin, while the south is high and heavily cratered. This dichotomy might result from a giant impact early in Mars's history. Venus is similar in size to Earth, and it probably experienced giant impacts during formation. But we don't know details because Venus's surface has been completely resurfaced by volcanism within the last billion years, erasing evidence of ancient impact. Venus also lacks a large moon. If Venus had a Theia-like impact, either the debris didn't coalesce into a moon, or the moon spiraled back into Venus and was destroyed. Or perhaps Venus's impact geometry was different, not producing a stable moon. Uranus has an extreme axial tilt, 98 degrees, meaning it essentially rolls around the sun on its side, its poles sometimes pointing nearly at the sun. This unusual tilt is best explained by a giant impact that knocked Uranus over early in its history. Uranus's moons might have formed from debris from this impact, similar to how Earth's moon formed. Pluto's large moon Charon is proportionally much larger relative to Pluto than our moon is to Earth. The Pluto-Charon system is sometimes called a binary planet because the center of mass around which both orbit lies outside Pluto's surface, in space between the two bodies. Charon likely formed from a giant impact into Pluto, perhaps during the late heavy bombardment, when large impacts were still common, even in the outer solar system. So giant impacts and the formation of large moons from impact debris are not unique to Earth. They're a natural consequence of planet formation, of the chaotic process by which planetary embryos collided and merged to form the planets we see today. Earth's moon is the most thoroughly studied example, but it's part of a broader pattern. This pattern extends beyond our solar system. As we've discovered thousands of exoplanets, planets orbiting other stars, we're finding that planetary systems are diverse, with architectures ranging from orderly to chaotic. Many exoplanets likely experience giant impacts during formation. Some might have large moons, possibly habitable, though detecting moons around exoplanets is extremely difficult with current technology. The search for exomoons, moons around exoplanets, is an active area of research. Large moons around planets in the habitable zone, the region where liquid water could exist on a surface, might themselves be habitable, might host life, might be more common than habitable planets. Jupiter's moon Europa and Saturn's moon Enceladus have subsurface oceans beneath icy shells, possibly habitable environment. If similar moons exist around exoplanets in habitable zones with thinner ice shells or even exposed ocean, they could be prime targets in the search for extraterrestrial life. Our moon is not habitable in any conventional sense. No atmosphere, no water, extreme temperatures, harsh radiation. But studying the moon teaches us about planet formation, about impact process, about the evolution of planetary body. The moon is a laboratory for planetary science, accessible enough that we can visit it, study it in detail, learn lessons applicable to understanding other worlds. Let's contemplate what it means that the moon exists because of a catastrophe, because of a collision so violent that it melted worlds, threw debris across space, fundamentally altered Earth's structure and composition. It's sobering to think that our existence, our planet's habitability, might depend on what appears to be an accident, a chance collision 4.5 billion years ago. If Theia had missed Earth, if the orbital dynamics had been slightly different, if Theia had been captured into orbit instead of colliding, or if it had struck at a different angle or velocity, the outcome could have been very different. Earth might not have a large moon. Earth's tilt might not be stable. Earth's day might be much longer or shorter. The distribution of volatile elements might be different, affecting ocean formation, atmosphere composition, climate. We can't know how these differences would have affected Earth's habitability, life's origin, evolution's trajectory. Perhaps life would still have arisen and evolved to produce being capable of asking these questions. Perhaps Earth would be sterile, inhospitable. Perhaps intelligent life would have evolved earlier, or later, or never. This is the anthropic principle in action, the observation that we can only exist in a universe, in a planetary system, on a world compatible with our existence. Of course, Earth has the properties necessary for life, because if it didn't, we wouldn't be here to observe it. The moon exists, and we can observe and study it, because the chain of events leading to its formation was compatible with our eventual evolution. But this doesn't make the moon any less remarkable, any less worthy of wonder and study. The moon is there, a testament to cosmic violence, to the chaotic process of planet formation, to the ability of nature to create order from destruction, to build new structures from the debris of catastrophe. The moon formed hot from molten material and cooled over millions of years. Life on Earth, when it eventually arose, emerged from chemistry, from simpler molecules building more complex, from self-replicating systems evolving into cells. Both the moon's formation and life's origin involved organization, structure emerging from disorder, complexity arising from simplicity. There's a poetry in this parallelism, in the idea that both our planet and our cosmic companion are products of natural process, of physics and chemistry operating over deep time. time, of order arising naturally when conditions are right. Neither required supernatural intervention, miraculous creation, designed by intelligence. Both are comprehensible, explicable through natural law, through processes we can study, model, understand. This is the power of science, to look at the world, to ask how it came to be, to develop explanations based on evidence and logic, to test those explanations against new observations, to refine our understanding iteratively. The giant impact hypothesis wasn't handed down from authority. It was proposed, debated, tested, refined, eventually accepted because it explained the evidence better than alternative, because it made predictions that were confirmed, because it withstood scrutiny, and the hypothesis continues to evolve. New simulations with better physics, new lunar samples analyzed with better instruments, new theoretical insight from studying other planetary systems all contribute to refining our understanding. Maybe in another decade or two, we'll have a different picture, a better model, more accurate detail. That's how science works. It's not about final answer, but about increasingly accurate approximation, progressively better understand. As we approach the end of this journey, let's reflect on what the moon represents, what it means for us as beings living on Earth, looking up at this ancient companion. The moon is a reminder of events that occurred billions of years before humans existed, before Earth was habitable, before the solar system was fully formed. When we look at the moon, we're seeing a body that has existed essentially unchanged for over 3 billion years, that has witnessed Earth's entire history, that was there when continents formed, when oceans filled, when life arose and diversified, when humans evolved and built civilization. The moon has seen everything. It's watched countless extinctions, ice ages, continental collisions, asteroid impacts, volcanic eruptions. It's seen the rise of dinosaurs and their fall, the evolution of mammals, the spread of forests and grassland, the appearance of humans. It's witnessed all of human history, from its origin in Africa to the present, the development of agriculture, the building of cities, the rise and fall of empire, wars and peace, art and science, joy and suffering. And through it all, the moon has changed minimally. New craters have formed, slowly, infrequently. The surface has been gardened by micrometeorite, mixing the regolith. But the major features, the Maria, the Highland, the large craters, have remained essentially constant, a stable backdrop against which Earth's drama unfolds. The moon is also a reminder of our interconnection with the cosmos, of the fact that we live in a universe of immense scale and antiquity, that our planet is part of a larger system, that events in space affect us profoundly. The moon's gravity raises tide, stabilizes our tilt, affects our culture. The sun provides energy for life. Asteroid impacts have caused extinction. Cosmic rays mutate DNA, driving evolution. We're not separate from the universe, but embedded in it, products of it, subject to its laws and influence. The moon demonstrates that we can understand the cosmos. Through observation, through reason, through science, we can figure out where the moon came from, how it formed, what it's made of, how it affects Earth. We can send spacecraft to orbit it, land on it, collect samples, bring them back for analysis. We can model its formation in computers, can test our models against evidence, can refine our understanding. This is extraordinary when you think about it. We're apes who evolved on the African savanna, whose brains developed to solve problems of survival, finding food, avoiding predators, cooperating with others. Yet, we can use those same brains to understand events that occurred 4.5 billion years ago, to comprehend processes involving temperatures of thousands of degrees and energies equivalent to billions of nuclear weapons, to figure out the history of worlds. The moon is also a symbol of possibility, of the future, of humanity's potential to become a spacefaring species. We've been there. We've walked on its surface, collected its rock, driven rovers across its plane. We can go back. We can establish bases, mine, settlement. We can learn to live off Earth, to use resources from other worlds, to become multiplanetary. Whether we should do this, whether it's wise or necessary or ethical, is debated. Some argue that we should fix problems on Earth before expanding into space. That space exploration is a distraction from urgent terrestrial concern. Others argue that becoming multiplanetary is essential for humanity's long-term survival, that all our eggs shouldn't be in one basket, that a single planetary catastrophe shouldn't be able to end human civilization. Both perspectives have merit. We should address Earth's problems: climate change, biodiversity loss, poverty, conflict. But we can also explore space, can expand our presence beyond Earth, can work toward a future where humanity is not confined to a single world. These goals aren't mutually exclusive. They can be pursued simultaneously. The moon, in this context, is a first step. It's close, accessible, relatively safe as extraterrestrial environments go. Learning to live on the moon, to extract resources, grow food, generate energy, recycle water and air, teaches lessons applicable to living anywhere off Earth, whether Mars, asteroids, or eventually other star systems. Imagine a future where people live on the moon, in habitats beneath the surface or in pressurized domes, growing plants in greenhouses, mining water ice from polar craters, using solar panels and nuclear reactors for power. Imagine looking up from Earth and seeing lights on the moon, cities perhaps, human civilization extending beyond its home world for the first time in a permanent, self-sustaining way. This future is speculative, uncertain, perhaps decades or centuries away, but it's not impossible. The technology exists or is being developed. The resources are there. The only question is whether we have the will, the vision, the persistence to make it happen. And if we do establish a presence on the moon, if humans become a two-world species, the moon's origin story becomes even more poignant. We will be returning to the debris of an ancient catastrophe, living on the remnants of Theia, walking on ground that was once molten rock thrown into space by the most violent collision in Earth's history. We'll be closing a circle, connecting present to past, living in the consequences of events that occurred 4.5 billion years before we exist. The moon, in all its ancient stillness, carries stories of formation and destruction, of heat and cold, of impacts and volcanism, of a time when the solar system was young and chaotic and dangerous. Stories of Earth's early history, preserved in lunar rock because they've been erased on Earth. Stories of cosmic violence creating cosmic beauty, of catastrophe giving birth to wonder. Every culture that has looked up at the moon has told stories about it. Ancient Mesopotamians tracked lunar phases, created calendar, worshipped lunar deity. The ancient Greeks had Selene, riding her chariot across the night sky. The Romans had Luna. Chinese mythology speaks of Chang'e, who drank an elixir of immortality and floated to the moon, where she lives forever in a palace with a jade rabbit. Native American tribes had names for each full moon: the wolf moon, the snow moon, the harvest moon, marking the passage of season. The moon has been a timekeeper, a calendar, a clock visible to everyone. Before artificial lighting, before clocks and watches, the moon was one of the few reliable ways to track time at night. A full moon provided light for travel, for work, for celebration. A new moon meant darkness, quiet, rest. The lunar cycle, 29.5 days from new moon to new moon, became embedded in culture, gave us the concept of the month, influenced religious observances, agricultural practices, social customs. The moon has been associated with madness. The word lunacy derives from Luna, the Roman moon goddess. The belief that the full moon affects human behavior, causing increased violence, accident, or mental disturbance, persists despite lack of statistical evidence. Studies have repeatedly found no correlation between lunar phases and crime rate, hospital admission, or psychiatric emergency, but the belief endures, perhaps because humans are pattern-seeking creatures, because we remember the dramatic incident that happened during a full moon and forget the quiet night when nothing unusual occurred. The moon has been a symbol of femininity in many cultures, associated with menstruation, because the lunar cycle and menstrual cycle have similar length, though this is likely coincidental. The moon waxes and wanes, grows and shrinks, cycles through phases, all of which have been seen as feminine quality, contrasting with the sun's constant masculine brightness. The moon has inspired poetry, art, music across every culture and era. From ancient Sumerian hymns to modern pop songs, the moon appears as a subject, a metaphor, a backdrop. It's been a symbol of loneliness, of longing, of romance, of mystery. Once in a blue moon means something rare. Shooting for the moon means aiming high. Mooning over someone means pining with unrequited love. The moon pervades our language, our idiom, our metaphors. The moon has also been a scientific instrument. By observing how the moon moves, how it orbits Earth, how its position changes relative to the star, early astronomers learned about celestial mechanics, about gravity, about the nature of the solar system. The moon's motion helped confirm Kepler's laws of planetary motion, helped Newton develop his theory of universal gravitation. Lunar eclipses, when Earth's shadow falls on the moon, provided evidence that Earth is round. The shadow is always circular, regardless of where in the sky the eclipse occurred. Lunar eclipses also allowed ancient astronomers to estimate Earth's size. The Greek astronomer Aristarchus, in the 3rd century BCE, used the geometry of lunar eclipse to estimate the relative sizes of Earth, moon, and sun, and the relative distances between them. His estimates were remarkably accurate, given the limitations of his instruments and method, demonstrating that careful observation and geometric reasoning can reveal truths about the cosmos. The moon has also served as a Rosetta Stone for planetary science. Because the moon preserves a record of early solar system history that Earth has lost, because its surface hasn't been reworked by plate tectonics or obscured by an atmosphere, studying the moon tells us about processes that affected all the terrestrial planets. The Late Heavy Bombardment, a period of intense impacts between about 4.1 and 3.8 billion years ago, is recorded in lunar rocks and craters. This bombardment affected Earth too, possibly destroying early life if it had already arisen, possibly delivering water and organic molecules that helped life get started. The moon's cratering record has been used to calibrate impact rates throughout the inner solar system. By dating lunar rocks brought back by Apollo and correlating those dates with crater densities at the collection sites, scientists developed a chronology relating crater density to age. This lunar cratering chronology can then be applied to other bodies, Mars, Mercury, asteroids, allowing geologists to estimate surface ages based on crater count, even without sample return mission. This technique isn't perfect. It assumes that impact rates have been similar across the inner solar system, which isn't exactly true. Jupiter's gravity affects the orbits of asteroids and comets, funneling some toward the inner planet, potentially creating different impact rates at different locations. But the lunar chronology provides a baseline, a reference against which other surfaces can be compared. The moon has taught us about volcanism on airless bodies. The mare basalt, those dark plains filling ancient impact basins, formed from lava flows quite different from terrestrial volcanism. With no atmosphere to provide pressure, lunar eruptions were probably fire fountains, sprays of molten droplets thrown high above the surface, falling back as glass beads and fragments. Some of these beads, found in lunar soil samples, contain tiny bubbles of volcanic gas trapped when the droplets solidify, providing information about the composition of the moon's interior and the conditions of eruption. The moon has taught us about space weathering, the gradual alteration of surface exposed to the space environment. Solar wind particles, mostly protons and electrons, constantly bombard the lunar surface. Cosmic rays, high-energy particles from supernova explosions and other energetic events strike the surface. Micrometeorite, dust grain-sized fragments of asteroids and comets, pepper the surface at velocities of tens of kilometers per second. These processes darken the surface, break down minerals, create nanophase iron particles that absorb light, amorphize crystal structure. Understanding space weathering is important for interpreting observations of asteroids and other airless bodies. When we observe an asteroid spectrum, the way it reflects sunlight at different wavelengths, we're seeing a weathered surface, not fresh material. To understand the asteroid's composition, we need to account for weathering effects, and the moon provides a laboratory where we can study these effects in detail, with samples we can analyze in the lab. The moon has taught us about tidal forces, about how gravitational interactions between bodies can dissipate energy, transfer angular momentum, circularize orbit. Jupiter's moon Io is the most volcanically active body in the solar system. Its interior continuously melted by tidal heating from Jupiter's immense gravitational pull. Saturn's moon Enceladus has geysers erupting from its south pole, spewing water ice into space, again driven by tidal heating. Understanding Earth-Moon tidal interactions helps us understand these exotic systems, predict their behavior, interpret their observation. The moon has been a testing ground for space exploration technology. The Apollo missions developed life support systems, spacesuit, navigation technique, landing procedures, all of which inform current and future missions. The lunar roving vehicle, those dune buggies driven by Apollo 15, 16, and 17 astronauts, demonstrated that wheeled vehicles could operate on extraterrestrial surfaces, paving the way for Mars rovers decades later. The moon has been a proving ground for international cooperation. While the Apollo missions were driven by Cold War competition, more recent lunar exploration has been increasingly collaborative. The International Space Station, while not lunar, established frameworks for multinational cooperation in space. Future lunar missions envision partnerships between space agencies, between nations, between government and private entities. The Artemis Accords, established by NASA and partner nations, set principles for lunar exploration: peaceful purpose, transparency, interoperability, emergency assistance, registration of space objects, release of scientific data, protection of heritage sites, extraction and utilization of space resources, deconfliction of activity, orbital debris mitigation. These principles aim to prevent conflict, ensure safety, promote cooperation, and establish norms for behavior on and around the moon. Whether these principles will be effective, whether nations will adhere to them when commercial interests are at stake, when resources are being extracted, when territory is being claimed, remains to be seen. Space law is still evolving, still being tested, still adapting to new reality. The Outer Space Treaty of 1967 established that celestial bodies cannot be claimed by nations, that space exploration should benefit all humanity, that weapons of mass destruction cannot be placed in space. But the treaty was written before commercial space activities were feasible, before resource extraction was practical, before the current resurgence in lunar exploration. As humans return to the moon, as we potentially establish permanent bases, as we begin extracting resources, legal and ethical questions will arise. Who owns lunar resources? Can companies claim mining rights? How do we prevent environmental damage, preserve scientific sites, protect the moon's historical and cultural value? These questions don't have clear answers yet, but they'll need to be addressed as lunar activities expand. The moon also raises philosophical questions about our place in the universe, about our relationship with nature, about progress and exploration. Should we go to the moon? Should we alter it, mine it, potentially pollute it? Or should we preserve it as a pristine wilderness, a monument to natural processes, a place undisturbed by human activity? There's a tension between utilization and preservation, between seeing the moon as a resource to be used and seeing it as a heritage site to be protected. This tension exists on Earth too. Wilderness preservation versus development, conservation versus exploitation. But on the moon, it takes on new dimensions because the moon has no indigenous life, no ecosystems to protect in the biological sense. But it does have scientific value, cultural significance, and a kind of pristine beauty that would be lost if it became industrialized. Some argue that humans have a responsibility to expand into space, to become a multi-planet species, to ensure our long-term survival, and that the moon is a necessary stepping stone. Others argue that we should first prove we can live sustainably on Earth, can manage our home planet responsibly before we export our problems to other worlds. Both perspectives have merit. We do face existential risk, asteroid impact, climate change, nuclear war, pandemic that could devastate or end human civilization. Establishing a presence on the moon or Mars provides a backup, a lifeboat, insurance against single-point failure. But we also need to be good stewards of Earth, need to address the urgent challenges we face, need to demonstrate wisdom and foresight before we expand our footprint beyond our home world. The moon in this debate is both symbol and reality. Symbolically, it represents humanity's aspiration to explore, to expand, to transcend our limit, to reach for something beyond ourselves. Realistically, it's a specific place with specific challenges and opportunity, a nearby world where we can test technology and develop capability for deeper space exploration. Perhaps the answer isn't either or, but both and. We can work to solve Earth's problems and explore space. We can preserve parts of the moon while developing others. We can extract resources where it makes sense while protecting scientifically and culturally significant sites. The moon is large, about the same surface area as Africa and Australia combined, with room for multiple uses, multiple values, multiple approaches. Let's think about what future lunar explorers might discover, what mysteries remain to be solved, what questions we haven't yet thought to ask. Despite 6 Apollo landings, despite dozens of robotic missions, the moon still holds secrets. The moon's interior structure is still not fully understood. We have seismic data from only 4 Apollo seismometers, operating for only a few years, insufficient to map the interior in detail. We know there's a crust, mantle, and core, but the exact boundaries, the composition at different depths, the presence of partial melt zone, the size and state of the core, all these remain uncertain. Future missions, with networks of seismometers operating for years, could create detailed 3-dimensional maps of the lunar interior, revealing structure and composition with precision. The moon's far side, especially the South Pole Aitken Basin, is intriguing. This enormous impact crater, over 2,000 kilometers in diameter and up to 8 kilometers deep, may have excavated material from the moon's deep crust or even the upper mantle. Studying rocks from the basin floor could provide samples of the lunar interior without having to drill, offering insights into the moon's composition and differentiation. The basin also shows unusual mineral compositions, with elevated concentrations of iron and titanium, possibly indicating exposed mantle material. But interpretations are complicated by the fact that the basin has been filled with basaltic lava flows, overprinting the original impact material. Disentangling impact ejecta from volcanic material requires careful fieldwork. detailed sampling, laboratory analysis, work best done by humans on the surface. The moon's permanently shadowed regions, craters near the poles that never see sunlight, harbor water ice, and possibly other volatile materials. These cold traps have been accumulating material for billions of years, potentially preserving a record of volatile delivery to the inner solar system, of cometary composition, of the history of water in the Earth-Moon system. Sampling these deposits could reveal when water began arriving, where it came from, how much has been delivered over time. The water ice in these cold traps is also practically valuable. Water is heavy, expensive to launch from Earth. If lunar water can be extracted, purified, and used for life support, or split into hydrogen and oxygen for rocket fuel, it reduces the cost and complexity of lunar operations dramatically. A lunar base with local water resources is much more feasible than one dependent on water shipped from Earth. Extracting lunar water isn't trivial. The ice is mixed with lunar regolith, probably in low concentration, frozen solid at temperatures around 40 Kelvin, 233 degrees Celsius. Mining and processing this material, separating ice from rock, melting and purifying the water. All this requires energy, equipment, engineering, but it's doable with current or near-term technology, and multiple space agencies and companies are developing systems to do exactly this. The moon may also contain helium-3, a rare isotope that is scarce on Earth but more abundant in the lunar regolith. Because it's implanted by the solar wind, helium-3 is proposed as fuel for fusion reactors, which would produce energy without radioactive waste, a potentially clean, inexhaustible power source. But fusion power using helium-3 is still theoretical, decades away from practical reality if it's ever achieved. And extracting helium-3 from lunar regolith would require processing enormous volumes of material for relatively small returns. So while helium-3 is often mentioned as a reason to return to the moon, it's not a near-term justification. More immediate are resources like water, metals, and building materials. Lunar regolith can be used for radiation shielding, for building material if sintered or processed into bricks, for covering habitats to protect them from micrometeorites and temperature extremes. Iron, titanium, aluminum, and other metals can potentially be extracted from lunar minerals, though the energy requirements are substantial. The moon's lack of atmosphere and stable surface make it ideal for certain types of scientific facilities. Telescopes on the moon's far side would be shielded from Earth's radio emissions, providing a quiet environment for radio astronomy. Infrared telescopes in permanently shadowed craters could observe the universe at temperatures naturally achieved without active cooling. Interferometers with baselines of hundreds or thousands of kilometers could achieve angular resolutions impossible from Earth or single spacecraft. Particle physics experiments might benefit from the moon's environment. The vacuum is better than what's achievable in laboratories on Earth. The seismic stability, especially in certain locations, is excellent. Detectors buried beneath the lunar surface could be shielded from cosmic rays, useful for detecting rare processes like proton decay or searching for dark matter. The moon could host laboratories for materials science, manufacturing, growing crystals, or producing alloys under conditions impossible on Earth. Microgravity research is currently done on the International Space Station, but the ISS is expensive to access and has limited space. The moon provides stable facilities, potentially lower launch costs if infrastructure is developed, and access to local resources. Biosphere experiments on the moon could test closed-loop life supports, growing food in greenhouse, recycling air and water, developing sustainable habitats. These experiments are relevant for Mars mission, for space station, for any long-duration space mission. The moon is close enough that resupply is feasible if something goes wrong, making it a safer test bed than Mars. Art and culture might find expression on the moon. Imagine sculptures created from lunar regolith, art installations using the stark landscape, performances in the low gravity, music composed and recorded in lunar habitat. The first extraterrestrial art, the first off-world culture beginning to develop distinct identity, aesthetic value. This might sound fanciful, but humans are creative beings. Wherever we go, we create culture, express ourselves, make art. The moon won't be just a workplace, just a mining outpost, just a science station. It will be a place where people live, work, dream, create. And in doing so, they'll make the moon not just a destination, but a home. Let's return to the story of the moon's formation, synthesize what we've learned, reflect on the meaning and significance of this ancient event. The moon formed 4.5 billion years ago from debris created when a Mars-sized body called Theia struck the young Earth in a glancing collision. The impact melted both worlds, threw enormous amounts of material into space, and from that debris, the moon coalesced. This isn't just a dry scientific fact. It's a profound statement about the nature of the solar system, about how planets form, about the role of chance and violence in creating the worlds we see. The moon exists because of a catastrophe, because of what appears to be an accident, a random collision in the chaotic early solar system. But perhaps accident isn't the right word. Collisions between planetary embryos weren't rare during the late stages of terrestrial planet formation. They were expected, inevitable, part of the process. The specific timing, the specific angle, the specific masses involved, those might be chance. But that giant impacts occurred, that they shaped the final configurations of planet, that they left lasting consequences, that was built into the physics of planet formation. The moon is evidence of this process. It's a frozen record of an event we can never directly observe, a body we can study to understand not just its own history, but the history of all terrestrial planets, the processes that shaped the inner solar system. And the moon continues to be relevant. It affects Earth's tides, climate, rotation rate. It provides light at night, creates eclipses, serves as calendar and timekeeper. It inspires culture, art, science, exploration. It's a destination for future missions, a potential home for human outposts, a stepping stone to deeper space. The moon is old. It's a remnant of Earth's violent infancy, a companion that has witnessed our planet's entire history. It was there when Earth's crust first solidified, when oceans condensed, when the first life arose in those oceans. It watched continents form and break apart, watched life diversify and colonize the land, watched organisms evolve from simple cells to complex ecosystems. The moon saw the great oxygenation event 2.4 billion years ago, when photosynthetic bacteria filled the atmosphere with oxygen, fundamentally transforming Earth's chemistry and enabling complex life. It saw the snowball Earth episode, when ice covered the planet from poles to equator. It saw the Cambrian explosion, when animal life diversified rapidly. It saw the colonization of land by plants and animals. It saw the rise of dinosaurs and their extinction, the rise of mammals, the evolution of humans. And through all this, the moon remained essentially unchanged. Its surface was bombarded occasionally by new impacts, adding craters to the ancient landscape. But the major features, the Maria, the highlands, the ancient basins, remained constant. The moon is a stable point of reference in a changing world, a reminder that while Earth's surface is dynamic, transformed repeatedly by geological and biological processes, not everything changes. Not everything is temporary. There's comfort in that, perhaps. In a human life filled with change, with uncertainty, with impermanence, the moon is constant. The same face that looked down on ancient Sumerians, on Egyptian pharaohs, on Chinese emperors, on Roman senators, on medieval peasants, on Renaissance artists, on Victorian scientists, that same face looks down on us today. And it will look down on our descendants, on whoever comes after us, on future civilizations we can barely imagine. The moon is a witness. It has seen everything Earth has done, everything that has happened on our planet, all the triumphs and tragedies, all the beauty and horror of Earth's history, and it remembers, in a sense. The moon's rocks contain isotopes created by cosmic rays, accumulated over billions of years, recording the flux of radiation through space. The moon's craters record the history of impact. The moon's Maria record ancient volcanism. The moon is an archive, a library written in stone, and we can read that library. We can visit the moon, collect samples, analyze them in laboratories, extract information about the past. We've begun this process with Apollo, but we've barely scratched the surface. There's so much more to learn, so many questions to answer, so many mysteries to solve. What was Earth like before the moon formed? What was Theia's composition? And where did it form? Did the impact trigger plate tectonics on Earth? Or did plate tectonics develop independently later? How did the moon's magma ocean crystallize? And what does that tell us about its interior? When did the moon's volcanic activity cease? And why? What caused the bombardment 3.9 billion years ago? And did it affect Earth's early biosphere? These questions motivate continued exploration, continued study, continued investment in lunar science. The moon isn't just a historical curiosity. It's a key to understanding Earth, the solar system, the processes that created the worlds we see. As we close this journey through the moon's history, let's reflect on the perspective it provides. Looking at the moon, understanding its origin, contemplating the timescales involved, offers a kind of cosmic perspective that's both humbling and exhilarating. Humbling because it reminds us how small we are, how brief our existence, how recent our presence on Earth. Humans have existed for perhaps 300,000 years, civilization for perhaps 10,000 years, industrialization for 200 years. Against the moon's 4.5 billion year history, human existence is a blink, barely noticeable, a thin veneer of consciousness appearing in the last fraction of a percent of the moon's lifetime, but also exhilarating because we can understand this history, can piece together what happened, can figure out through observation and reason and science that the moon formed from a giant impact, that it was once molten, that it evolved over billions of years, that it shaped Earth's environment, that it influenced life's evolution. An ape species on one small planet, existing for a cosmic instant, can comprehend events that occurred billions of years before it evolved. That's extraordinary. The moon tells us we're part of something larger than ourselves, something older and grander and more epic than any human story. We're part of the universe, products of its process, subject to its laws, participants in its evolution. Our atoms were forged in stars, our planet assembled from debris, our moon created by catastrophic collision, our existence contingent on chains of events stretching back to the Big Bang. But we're also observers of the universe, questioner, understander. We can look at the moon and ask where it came from. We can develop hypotheses, test them, refine our understanding. We can appreciate the beauty of the moon, not just aesthetically, but intellectually, understanding the process that created that beauty, the history written in its features, the story it tells about cosmic evolution. The moon reminds us that destruction can create beauty, that catastrophe can lead to creation, that order can emerge from chaos. The moon formed from one of the most violent events in Earth's history, from an impact that melted world through debris across space, fundamentally altered both bodies. But from that violence, something beautiful emerged, a companion for Earth, a light in the night sky, a body that has shaped our planet's environment and influenced life's evolution. This pattern repeats throughout the universe. Stars form from collapsing clouds, a process driven by gravity's inexorable pull. Stars die in supernova explosion, violent events that destroy the star but scatter its enriched material into space, seeding future generations of stars and planets. Black holes form from the collapse of massive stars, extreme objects that warp space-time, but also serve as engines of galaxy evolution, regulating star formation, driving jets of energy across cosmic distances. The universe is both destructive and creative, violent and generative. The moon is a local example of this universal pattern, a nearby reminder that creation often requires destruction, that new structures emerge from the remnants of old ones, that the universe continually transforms itself. As you drift towards sleep tonight, perhaps you'll look out your window and see the moon, hanging in the sky as it has for billions of years. Perhaps you'll think about Theia, about that ancient collision, about the debris ring that formed and coalesced into the moon. Perhaps you'll appreciate the moon not just as a beautiful object, but as a storyteller, a witness, a key to understanding Earth's past and future. The moon is patient. It doesn't rush. It continues its orbit, continues its slow recession, continues its influence on Earth's tides and climate and rotation. It will be there tomorrow night and the night after, and for billions of nights to come. It will watch over Earth as continents drift, as species evolve, as civilizations rise and fall, as humans perhaps spread beyond Earth, perhaps establish homes on the moon itself, perhaps continue the story of exploration and understanding that brought us from wondering about the moon's origin to walking on its surface. The story of the moon is the story of Earth, the story of the solar system, the story of cosmic evolution. It's our story too, because we're part of this process, participants in this grand narrative. We're made of star stuff. As Carl Sagan famously said, we're the universe becoming aware of itself, asking questions, seeking answers, appreciating beauty, creating meaning. The moon, shining in the night sky, reminds us of all this. It's a beacon, a companion, a teacher. It's been there throughout Earth's history, and it will be there long after we're gone. But for now, in this brief moment of cosmic time, we can appreciate it, study it, understand it, and perhaps, someday soon, return to it. Thank you for joining me on this journey through the moon's history, from the violent collision that created it to its current presence as Earth's faithful companion. May you look at the moon with new eyes, with deeper appreciation, with a sense of connection to the ancient processes that shaped our world. May you find peace in the knowledge that we're part of a story much larger than ourselves, a story that continues to unfold, that we can witness and understand and appreciate. Good night, and may the moon light your way through whatever darkness you face, as it has lit the way for billions of years, as it will continue to do for billions more.